In the second part of Lesson 4.6, we will multiply and divide complex numbers. When multiplying with I, we'll treat it like a variable. We can multiply it by a number and we can multiply it by another I. Similar to x, if we multiplied x times x, we would get x squared. Similarly, if we took I times I, we would get I squared. Now, I squared is actually a definition. It actually becomes a real solution. I squared is equivalent to -1. Knowing this will be helpful when we create products and try to write our complex numbers in standard form. Let's try some examples on the right. We are asked to multiply and write our answers in standard form of a complex number. In the first product, we have I on the outside times the complex number 3 minus 8i. The I out in front would be an example of the distributive property, which means we're going to multiply I times 3, and since they're not like parts, that just stays the product 3i. And then minus I times 8i, and that would be 8i squared. We've completed the product by eliminating the parentheses, but now recognize that I squared is equal to -1. That means we can substitute -1 in place of I squared. From here, we're just going to kind of clean this up and get it in standard form. 3i will stay as is for now, but -8 times -1 is +8. Now this is the opposite order for standard form. All we need to do is flip it around. 3i plus 8 is equivalent to 8 plus 3i. Oops, I'm going to rewrite that I a little bit better. There we go. 8 plus 3i, and there's our product in standard form. In example B, same idea, very similar process. Now we have -4i as our number out in front times the complex number 2 minus 3i. Distribute the -4i in. -4i times 2, we can multiply the numbers to get -8i. And then -4i times -3i becomes +12, and then I times I is again I squared. Recognizing that I squared is going to equal -1, I'm going to substitute that in its place, and then let's clean this problem up. -8i, and then +12 times -1 would be -12. Again, in this form, our number is reversed for the standard form of a complex number. When I rewrite it, notice your A value is negative, and your BI value has a negative coefficient. -12 minus 8i. Typically, the biggest challenges I see as a teacher when I look at students' work is remembering that you have I times I sometimes when you do these products, and then that I squared always equals -1. In this example, we have two complex numbers that we're going to FOIL. I'm going to start with the 2 and distribute it to the 3. 2 times 3 is 6, and then I have minus 2 times 2i would be -4i, or 6 minus 4i. And then I'm going to take my 6i and distribute it to both parts. 6i times 3 is +18i. And again, watch what happens here, everybody. 6i times -2i would be -12i squared. So we have a couple of things happening here. I know my I squared is going to equal -1, but we also have like terms in the middle. So I'm going to start with my 6 and then recognize that my two terms in the middle both have a variable I, so I'm going to combine their coefficients. -4 plus 18 is +14i. And then -12, I squared equals -1. That technically changes my -12 to +12. And now the 6 out in front and the 12 at the end combine to be the total A value in our complex number. 12 plus 6 is 18, plus 14i, and there's our product in standard form of a complex number. Watch what happens when the complex numbers look similar, but the only difference is there's a positive and a negative in between the A and BI values. Again, we're going to start this one just like we did example C. I'm going to take the 5 and distribute it to both parts in that second parenthesis. 5 times 5 is 25, minus 5 times 9i would be 45i. Then if we take the 9i and do the same thing, positive 9i times 5 would be positive 45i, and then 9i times negative 9i would be negative 81i squared. Again, recognizing that I squared is going to have an impact on our solution, and negative 45i plus 45i. So watch what happens here. We'll start with our 25. What do you notice about the two I terms? Do you see that they both have the same coefficient but opposite signs? That means they're going to cancel out. And this idea is going to be helpful when we work on division down below. The idea of having the same numbers but just opposite signs in between them. Anyway, carry on. Then we have minus 81, and then I squared equals negative 1. Ultimately, then, what happens is that the negative 81 is going to change to positive 81. And that gives us 25 plus 81. And that would be an answer of 106. Notice the I term is missing. But in standard form, I need my placeholder. So if the I term is missing, that means B equals 0. We have to write plus 0i if we want to write our answer in full standard form. And last but not least in this section, if we have 6 minus 3i squared, this is going to be just like it would be if we had x in our expression somehow being squared. There should be 2 parentheses here, which means we have to write it twice and follow the processes for examples C and D. So I'd like you to pause the video and see if you can create this product. Combine like terms, write your answer in standard form. When you think you have it, press play and let's see how it went. Were you able to get 27 minus 36i? Looking at the FOIL up above, in this example, those two middle terms actually do not cancel. Please be careful as you're doing that FOIL process. And negative 3i times negative 3i gives us plus 9i squared for that last term, which then ultimately changes it to negative 9 because I squared equals negative 1. Combining your a values, you should have ended up with 27 minus 36i. And those are just a variety of examples of when we multiply. Let's finish up with division. When asked to divide with complex numbers, we technically actually don't do division. It's almost like dividing by a fraction where we change it to multiply by a reciprocal. We technically don't divide the fractions. It's a very similar idea. It's going to turn into a product, and that product is going to be related to the conjugate of the denominator. So the conjugate, if we take a complex number in standard form, no matter what it starts out in between, a conjugate just changes the sign in between. So it goes from one sign to the other. Everything else will stay the same. And how we use that is we take the denominator and multiply by the conjugate. So in a fraction with complex numbers, multiply the denominator by its conjugate. And ultimately, we'll end up multiplying both top and bottom by that value. For these final 3 examples, we'll start small and work our way up to more challenging complex number fractions. We're just asked to divide and write our answer in standard form of a complex number. The ultimate goal is to get I out of the denominator. So the conjugate is just going to be the opposite sign of whatever the imaginary part is. For example, if we just have negative 3 divided by I, the conjugate of positive I would be negative I. And if I multiply by that on the bottom, we also have to multiply by that on the top. It's just like changing a fraction to have a common denominator. We don't want to multiply one part and not the other. Once you multiply by the conjugate, we just simplify. In the numerator, negative 3 times negative I would be positive 3i. But in the denominator, I times negative I is negative I squared. And we know that I squared is a definition. I squared equals negative 1. That would give us 3I over negative 1, which ultimately cancels that out, giving us 3I over 1, or just 3I. Now, as a complex number, if the first term is missing, we need a placeholder. So we would put a 0 there. 0 plus 3I would be our division answer, or our quotient, in standard form of a complex number. As we progress to a different type of denominator, 1 minus I is a true complex form, or in true complex form. The conjugate, though, is what we need to multiply the denominator by to get rid of i's on the bottom. This means we're going to have to put a parenthesis around that and multiply by 1 plus I. That's the conjugate. You just change the sign in the middle. And just like with any fraction, again, whatever you multiply on the bottom, we have to multiply by on the top. Now we're only multiplying by 5 on the top. It's pretty easy to simply distribute that in. 5 times 1 is 5. 5 times I is 5I. And that's really all you have to do. There's nothing else that changes in the numerator. In the bottom, if we FOIL, 1 times 1 is 1. 1 plus I is plus I. Negative I times 1 is minus I. So be careful with your i's and your 1's here. Make sure your i's are prominent. And then negative I times positive I is negative I squared. Now we can simplify in the denominator just like we did up above when we FOILed. Positive I times negative I is going to cancel out. And I squared equals negative 1. This gives us 5 plus 5I over 1 minus negative 1, which is 1 plus 1. And that gives us a denominator of 2. When you multiply by the conjugate, notice what happened. Our i's went away in the denominator. So that's all fine and good to this point, but put a big star right here because this isn't our final answer, unfortunately. If we want to write in the standard form of a complex number, we really have to actually split the fraction up. Oh, I don't want that I don't want that there. Hang on. Sorry, I want that to be before the plus sign. Sorry about that. So I'm going to circle my 5 over 2. That's technically like the a part of our complex number. And then I'm going to put plus in between and take the second part of the fraction, the bi over 2. So that's 5i over 2. There's our separated complex number in standard form. Now watch what happens when we have a complex number in the numerator and the denominator. Here's what won't happen. These i's won't cancel out. I know it's kind of a bummer, but the addition and the subtraction really kind of change the meaning of each of the complex numbers. We want to stick with our definition of multiplying by the complex conjugate in the denominator. If we have 4 minus 5i, the conjugate is going to be 4 plus 5i. And this is where things are going to get a little messy. If we have 4 plus 5i on the bottom, we have to put 4 plus 5i on the top. We already have a true complex number on the top. That means we have to FOIL the numerator and the denominator. So these would be the most time-intensive problems that you'll see today. But you know how to do it because ultimately it just turned back into multiplication. So 3 times 4 plus 3 times 5i, 15i, 2i times 4, 8i, and then 2i times 5i is positive 10, I squared. There'll be some things that we can do to simplify that in just a moment. In the denominator, FOIL again, so 4 times 4 is 16, 4 times 5i plus 20i, negative 5i times 4 minus 20i, and negative 5i times positive 5i would be negative 25i squared. Now, just looking at the numerator, let's see what we can do. I see the 12, and then I see 15i plus 8i, and that would give us 12 plus 23i. And then notice, everybody, we've got our I squared hanging out over here. So plus 10 times negative 1. all over in the denominator. Again, watch what happens with our i's. Positive 20i minus 20i cancels, giving us 16 minus 25 times negative 1. As we think about combining our like terms, our 12 and our 10 times negative 1 would be 12 minus 10, which is 2. And that gives us a complex numerator of 2 plus 23i. Now in the denominator, negative 25 times negative 1 becomes positive. 16 plus 25 would give us 41. 2 plus 23i all over 41. Last but not least, let's split that. We're almost done. I know this is taking forever. 2 over 41 is going to be the a part of our complex number, plus 23i over 41. That's the bx, or the bi part of our complex number. And that's division. Overall, in lesson 4.6, we learned how to represent an imaginary solution with I. We did the 4 basic operations with complex numbers: addition and subtraction, multiplication, and division.